Hello. Yeah, I think we're ready now. So, welcome to this tutorial on vectors from the additional mathematics course. We'll be going over what you need to know in terms of vectors and how they work and how operations work with them and all of that in just a moment. This is obviously a live stream, so if you have any questions, just ask using the chat. Hopefully my audio is working and everything. If it's not, just let me know. Just let me know if you can hear me, so I know that that's the case. So I'm just checking the chat here. Hopefully people can hear me. So I don't know if people can hear me. We are ready to begin. Okay. Can you hear me though? Let me check. Okay, that's perfect. So we can begin now. Right. So today we'll be going over vectors. This is a topic, as I said, in additional mathematics. It's one of the most interesting topics in my opinion. It's not something that you meet before this point, I think, as opposed to some of the topics in algebra and like sequences and progressions and all of that. So first of all, we want to go over what is a vector. So let's just cover that. Oh, let me change the color. So the question is, what is a vector? Hopefully the chat can see this. I'll check the chat every once in a while. I don't have it in front of me, just to make sure everyone can hear us. Okay, that's perfect. So what is a vector? Well, a vector is it's like an arrow. You can think of it as an arrow. So it's a quantity with both a magnitude and a direction. So it's a quantity with both a magnitude and direction. And now the classical example that's given in this case is, the difference between speed and velocity. So when you talk about speed, you so you can say that a car is traveling at 25 kilometers an hour. That's just a speed. You get no sense of is it traveling north, is it traveling south, east or west, or at what bearing or any of that. You just know the raw value of its speed. On the other hand, a vector, as we said, it's a quantity with both a magnitude and a direction. So what the vector does is it does give you that value of 25 kilometers an hour, but added to that, it will give you the direction. So I would give you, so in this case, the vector quantity would be velocity, not speed. So we'd be careful to use the terminology correctly here. And we would say that the velocity of the car is maybe 25 kilometers an hour, say northeast, for example. So that's the first thing to clear up. But in mathematics, obviously, we don't want to keep on saying 25 kilometers an hour at this bearing. So for example, let's take the example that we just talked about. So 25 kilometers an hour, let's say northeast. So what does that mean? Well, it means that it's traveling at a velocity, at a speed of 25 kilometers an hour. So if we draw the speed sort of arrow, or the velocity arrow for that car, and then we can say that it's we also know that it's traveling northeast. So what's northeast? Well, it's it's sort of right in between north and east, and so we can say that if this horizontal line at the bottom here was east, and this this vertical line here was north, then we'd know that this is 45 degrees. right? So if I wanted to describe the velocity of the car, I can say something different now. I can say that it's traveling at 25 kilometers an hour clockwise from north, right? So I can say that it's 45 degrees clockwise from north. That's something else that I can say. So instead of giving, some sort of letters to go with the 25 kilometers an hour in order to describe the direction, so instead of saying northeast, I give a more numerical and more understandable value here, which is the 45 degrees. But there's something even better that we can do, because sometimes, you do want to know the angle and the the size of the speed or of the velocity, 25 kilometers an hour in this case. But sometimes what you want to know instead is, how much to the east is it traveling, and how much north is it traveling. So, we can get this 25 kilometers an hour and 45 degrees a different way. We can get it by saying that, well, we travel a certain amount to the right and then a certain amount upwards, right? And using these two values of the amount we travel to the right and the amount we travel upwards, we can figure out, the 25 kilometers, using Pythagorex theorem, and we'll see how that works. But we can also figure out the angle, using basic trigonometry. But we'll cover all of that. So how can we do that exactly? Well, we can work in reverse, right? So we know that we have a right angle triangle here with a magnitude of 25 and an angle over here of 45 degrees. So the amount that we go to the right in order to reach the top of this arrow, the amount that we go to the right here is, well, it's 25 cosine of 45 degrees, right? Because what cosine is, adjacent over hypotenuse, and so, the adjacent is just the hypotenuse times cosine, right? So that should be clear. And so cosine of 45 degrees, that's, just root 2 over 2. And so this is our answer. And we know that, this is a isosceles triangle. We have 45 degrees on both sides. And so this will also be 25 root 2 over 2. We can also work it out using sine. But that's not my point today. My point today is talking about vectors. So how does this relate to the topic of vectors? Well, this simplifies our problem much more, because now what we can say is that the velocity of the car, so the velocity we can say is, well, it's 25 root 2 over 2 kilometers an hour to the right. So let me just write right here, plus 25 root 2 over 2 kilometers an hour upwards. Now, we have symbols for this right and up terms, and that's just the I. We just use I for this, and J. Note that this I here should not be confused with the square root of -1. This is not the same thing. It's just telling us that, this I means we go to the right, and this J means we go up. Obviously, if the J value over here or the I value were negative, then we go in the opposite direction. But again, we'll go over that. We also, what we can do is we can take out this kilometers an hour and just put it on the outside. We don't really care about the units that much. We know what the units are, and so we can just ignore that. So overall, the velocity we would say is 25 root 2 over 2I plus 25 root 2 over 2J. And then if we wanted to, we can just put all of that in brackets and say kilometers an hour. Now, this was all an example just for a car's velocity. Let me see if there are any questions here. Nope. Okay, so this was all an example just for the car's velocity. But this just introduces you to the idea of a vector. So what is the vector in this case? Well, it's this bit over here that we say is a vector. So this is a vector. It's something that has both a magnitude and a direction, because we can work out the magnitude from these two values that we have here, and I'll tell you exactly how we do that. And we can also work out the direction again from these two values. Yeah. And this might be a simpler way of thinking about vectors rather than a magnitude and an angle like we had above with the 25 and the 45 degrees. We can think about right and up, That might be a simpler way, but there's the other way as well with the the 25 kilometers an hour and the 45 degrees. But this is just a different way, and it turns out to be useful in different contexts. Like this is a more useful method in different situations. So let's get into notation. So how do we write down this sort of stuff? Well, I've just shown you one way we can write it down, right? We can say that we can use this I and j notation. So we can write it as ai plus bj. We can write the vector as ai plus bj. So that's saying that if we want to, if we want to travel across a vector, all we need to do is go a units to the right and b units up. Very simple. That's one way we can do this. Another way of showing exactly the same thing is using vector notation like this. So where, notice that there's no bar in the middle. It's just a at the top and b at the bottom. Be careful to have a at the top and b at the bottom, and that shows exactly the same thing. Another thing we can say is, if this point here was a and this point here was b, then the vector from a to b, so we're going from a to b, and we need to indicate the direction, so we just put an arrow on top of it like this, and that also denotes the same vector. Keep in mind that this only represents the vector. It doesn't actually tell you what the vector is, so what its value is. So we would say that AB arrow like this, or just AB, the vector AB is equal to AI plus BJ in this case, right, based on this. Yeah, so these are all the ways that we have, or all the ways that are relevant. So now let's look at certain cases. So now we have the foundations for what vectors are and how they work. Let's suppose we had two vectors like this. So let me draw an entire plane for you. And suppose we have on the x-axis here, and the y. Remember, the x-axis is the horizontal direction, so that we use the letter I for. But the axis itself is called x. It's only I that we use to denote the term right or left. If it's negative, and j is just used for up. So let me draw a scale here just very quickly. So suppose we had something like this. And suppose we had the point A here, and we have the origin, of course, and we usually denote the origin, so that's the point 0, 0 over here as O. And suppose we had the point A at 1, 1. Now, so this is an interesting situation. Now, let's think about what the vector OA looks like. So what does the vector OA mean first? Well, by the way, we denote it like this again, because we're going from O to A, and we'll do an arrow at the top, just to represent that this is a vector. So, and what does this mean? Well, this means that the vector OA means the amount by which we need to move to the right and the amount by which we need to move up in order to go from O to A. It's a very simple thing. So how do we calculate that? Well, we can see from the diagram here that we need to move 1 unit to the right in order to get to A, and 1 unit up in order to get to A. So 1 unit to the right in order to get to this bottom part, and then 1 unit up from O to A. So because we need to move 1 unit to the right, we say 1i, and because we need to move 1 unit up, we say plus 1j. Now let's look at a different example. Suppose we had the point B here at the bottom at 1, negative 1. Well, what can we do? Well, we can just we can repeat the exactly the same process. So again, how do we get from O to B? Well, we move 1 unit to the right, so that's 1i, and then we move this time 1 unit down. So that's not 1 unit up, that's 1 unit down. So it's down is the opposite of up, and so we denote that using the negative number. So it's minus 1j. So as though we're moving up negative 1 units. That should be quite basic. So let's do just one more example. So suppose we have the point C over here with coordinates 2, 1. This is the point C. Again, in order to get to the point C, and I encourage you to work with me on this, we need to, come on, you can say this, wherever you are. You can just try to guess the answer. You can just pause this for a second and try to figure out what it is. But in this case, again, we need to move 2 units to the right. So that's 2i, and then 1 unit up, which is 1j, which is very nice. Okay. So that's it. So what do we notice about all of these cases? Well, when the coordinates of a point A, for example, were 1, 1, the vector OA was 1i plus 1j, again, 1, 1. When the coordinates of B were 1, negative 1, the vector OB was 1i minus 1j, again, 1 minus 1, or 1, negative 1. When the coordinates of C were 2, 1, the vector OC was 2i plus 1j, which is 2, 1. So I think we can guess from here a general, a general thing, a general expression for the vector OD, where D is just the point xy. Again, as with all of these cases, what we can see is that the x-coordinate corresponds to how much we move to the right, and the y-coordinate corresponds to how much we move up. So in this case, we would get that OD, the x-coordinate here is just x, and so we get xi, and the y-coordinate here is just y, and so we would get yj. Now, why is this true though? We just showed that this is true for 3 examples. Why would this be true in general? Well, we can see that it would be true in general because, x is the x-coordinate of a point is exactly how much you need to move to the right from the origin in order to get to that point, right? That's literally its definition. If you kind of project this point onto the x-axis, you will get its x-coordinate. And this x-coordinate will be positive if we're moving to the right, and it will be negative if we're moving to the left. That's just how the axes are made. And similarly with the y-coordinate, again, it's literally defined as how much we need to move up or down in order to get to the point. So if we project D onto the y-axis, we will get its y-coordinate. And similarly, again, the y-coordinate will be positive if we need to move up, and the y-coordinate will be negative if we need to move down. And so we can see that the vector OD will indeed be xi plus yj, right? And so just to get comfortable with the different types of notation, again, this is just denoted also sometimes as just xy like this. Also with this, with the ones we had above, we can write this OA as 1, 1, OB as 1 minus 1. Remember, the j part goes down, and OC as 2, 1. So yeah, that's the situation. So that's how vectors work. So let's try to think about some situations. So suppose we had 2 parallel vectors. So actually, before we think about that, let's think about what if we did not start from the origin, okay? Let's think about the vector AB. What is the vector AB? Well, before we jump straight into thinking about the points A and the point B on this diagram above, let's think about what a vector means again. Well, a vector means what a vector says is the amount you need to move to the right and the amount you need to move up in order to go from the first point to the second point. So let's do that exactly. So by how much do we need to move to the right in order to go from A to B? Well, B is on the same location on the horizontal axis as A, right? You don't need to move right or left. Try it. If you move a bit right, you get further away from B, and if you move a bit left, you get again further away from B. And so, the amount you need to move to the right is 0. It's just 0. So we say 0i. Sometimes you can skip it. You don't have to write the 0i. You can just not write anything there, but we'll just write 0i for demonstration purposes. But suppose now let's think about the second part, because remember, it's not just about right and left, it's also about up and down. So by how much do we need to move up or down to get from A to B? Remember, it's from A to B, not from B to A. Why from A to B? Well, because the way we've written the vector here is A and then B, and the arrow goes from A to B, and so that tells us, we need to go from A to B. So we need to move 2 units down, we can see from the diagram, in order to go from A to B. And so the vector and so that part of the vector will be negative because we need to move down rather than up. And by how much will it be negative? Well, it will be negative 2 units. And so we will get negative 2j, right? Or again, we can write this as 0, negative 2, like this, using the different notation, right? So we can now think about vectors. So in this case, by the way, we would write the vector AB as, you go to the point A, you move down to the point B. I know this is getting slightly messy here. And then you draw an arrowhead, and that shows you the vector AB. So now we can think about vectors not just from the origin to a point, but also from points to other points. So suppose now we didn't have this diagram, and I just told you that the vector OA is, let's say, AI, A1I plus A2J, and that the vector OB is B1I plus B2J, just some general vectors. How can we find the vector AB? That's an interesting question. And in order to answer this question, we need to think about what we did in the special case we saw above. So in the special case we saw above, we had that OA was 1I plus 1j, and that OB was 1I minus 1j. If you look to the right here, we have OA is 1I plus 1j, and OB is 1I minus 1j. And then AB was just minus 2j, 0I minus 2j. Now, how can we relate these two to each other? How can we use OA and OB in order to get AB? Well, think about it. OA says that it's 1 unit from that the point A is 1 unit to the right from O, right? It's also 1 unit up, but let's focus on the right and left bit first. So it's 1 unit to the right from O. B is also 1 unit to the right from O. So what does this tell us? Well, the fact that they're both the same amount of units to the right from O tells us that they will be in the same position in the right or left, right? They will be in the same position on the horizontal axis. And that is the case in what we see here. We see that both A and B are in the same position on the horizontal axis. And we could figure that out just from looking at the difference between the horizontal positions of A and B based on these vectors, right? Because the difference between 1 and 1 here is 0, and so that tells us that A and B are in the same position on the horizontal axis. So what we needed to do in order to find, the vector AB, that 0 part of it, we just needed to look at the difference between the horizontal parts of the vector OA and the vector OB, because once we looked at the difference, 1 minus 1, that gave us 0. And taking the difference makes sense here because we're looking at how far away they are from the origin compared to each other. So if they're both the same amount away from the origin, if you're both 5 meters from a certain location and you're both to the right, like if you're both if two people are 5 meters to the right of a certain location, you can be sure that they are in the same location, right? That makes sense. And you do that by looking at the difference between how much they are to the right from that location, and in that case the difference is 0. Okay, now let's look at the vertical part. Well, the vertical part isn't as simple because we don't have the same value. And so the question is, do we do 1 minus minus 1, or do we do minus 1 minus 1, right? Well, what we see is that when we look at the vector AB, we see that it's 0I minus 2j. And so what we did was subtract, we did OB subtract OA in order to get that part of the answer. Okay, and so what it looks like right now is that AB, the vector AB, is always the vector OB minus the vector OA, right? And so is that true or is it not true? Well, let's figure it out. So suppose I had 2 points here, A, and B, and I had a point O, a reference point O. So what this equation is telling me is that in order to get from A to B, I need to first go to, so how we can think about this is, well, what happens if we rearrange the equation we have above? Well, if we rearrange the equation, because the minus is a bit uncomfortable, like we don't really know how to deal with that minus, how do we subtract a vector really? So we can just add OA to both sides, and so we get OA over here plus AB gives us OB. And our goal is to check whether or not this is true. So if we check that really quickly, so what this is saying is that if I take the vector OA and then I add the vector AB, I should get the vector OB. Yes, and that makes sense because, if you think about, again, the X and Y axes, if I move, say 2 units here, and then in order to go from A to B, I move another 2 units, well then, of course, the vector OB will be 4 units away, which is 2 plus 2. And then similarly, if I need to move 3 units up in order to get to A, and I need to move 2 units down in order to get to B, well then B will be 1 unit. B will be 1 unit above O, which is 3 plus minus 2, right? Which is 1. And so that is the case indeed. So we have this equation over here, which we can rearrange in order to get the above equation. So the above equation tells us about the relative vector, or kind of the vector just from A to B, if we know the vectors to each of the points separately from some reference point O. So we know that the vector AB is just OB minus OA. So it's always the one that comes second that comes first here. So you can think about it that way. So yeah, so it's just, if it's AB here, then it must be OB minus OA. Similarly, if we had CD, for example, then we get OD minus OC. Right? And we explained why that would be the case. All right, so that's it for now. That's it in terms of understanding vectors and understanding how they add together and how they come together. Now let's think about a few things. So firstly, what are parallel vectors? Well, as the name suggests, two vectors are parallel if two vectors are parallel if they have the same direction but different magnitudes. But they could have the different, just if they have the same direction. If they have the same direction, regardless of what their magnitudes are, they can be exactly the same vector as well and still be parallel. So, visually we can see whether or not vectors are parallel. So if I give you these two vectors, for example, you can tell me, yep, they're definitely parallel. So this is the vector AB over here, and this is the vector CD. And if I give you this vector and this vector, you'll tell me, nope, they're not parallel because they have a different direction. But how can we do that with our vector notation? Because we won't always have these diagrams. What we will have instead is these vector expressions for these different vectors, in terms of I and J notation. So in this case, suppose we in order to figure out whether two vectors are parallel, we need to check that they have the same direction, regardless of what their magnitudes are. So suppose AB was 2i plus 2j. In order to get from A to B, you need to move 2 units to the right and 2 units up. And suppose CD was also 2i plus 2j. You need to move 2 units to the right and 2 units up. Well, in this case, of course they would be parallel, right? Because they're basically exactly the same vector. And so, they are parallel. But suppose I change this 2 over here into a 3. Well, then CD in this case would be slightly steeper than AB. And so they would not be parallel in that case. But we don't always want to draw a diagram and think about steepness and all of that, and it might be complicated in other cases. So how can we use the numbers that we have here straight away in order to tell that they are not parallel? Well, what we can do is we can think about the gradient of a vector, or like the slope of a vector. So the slope of the vector AB over here is just the rise over the run. This is what we're used to. Slope is equal to rise over run. So in this case, the rise is exactly how much we go upwards. And in this case, we go upwards by 2 units, right? Because that's what this vector notation tells us. It tells us how much we go to the right by and how much we go up by. And so, the rise is how much we go up by, and so we can take that directly from here. And we know that the rise is 2, and the run is exactly how much we go to the left or right by. And we know here that we go to the right by 2 units, and so the run over here is positive 2 as well. And so the slope overall is just 1. Now, for CD, if we do the same thing, we get that the slope is 3/2. So the slopes are different. Now, if the slopes are different, we know that they don't have the same direction, and so they're not parallel. And this is the basic idea of how you figure out whether or not vectors are parallel. Now, let's look at something different. Let's consider how we find the magnitude of a vector. So, magnitude of a vector. So, in order to figure this out, let's just think about a general vector, right? Let's just think about, suppose the vector AB over here from a point A to a point B is xi plus yj. And again, just to remind you of the notation, this can also be written as this. So let's think about the magnitude of AB. Let's remind ourselves first of what the magnitude means. So suppose we had a vector AB like the one I've drawn here. The magnitude tells us kind of the length of this vector. It ignores the direction. Here we can see that it's kind of, if we had north here and east here, then we would know that AB is northeast. And, if AB was, if a car was traveling from A to B, along that direction at 25 kilometers an hour northeast, then that would be an entire vector. But if we only want the magnitude of that vector, we would only look at the 25 kilometers part. That's what we covered in kilometers per hour part. That's what we covered in the beginning. So in the beginning, we talked about that, but now we want to see how we can find the magnitude if we have a vector in this notation. So if I know that in order that AB, in order to get from A to B, or in order to travel in the direction AB, we need to go x units to the right and y units up. How do I figure out what the magnitude of AB is? And I think you can see what's coming, because here we have a right angle triangle. Why? Because the horizontal direction is perpendicular to the vertical direction by definition. And so if we want to find the magnitude of vector AB, we just need to find the length of this segment over here, the segment that takes us from A to B. And how we do that is using Pythagorex theorem, right? Because we just use Pythagorex theorem. So what does Pythagorex theorem say? Well, it says that the hypotenuse C squared is equal to the adjacent side A squared plus the opposite side B squared. So the squares on the sides add up to the square on the hypotenuse. And so that tells us that AB squared, and I'll just write it this way for now, is equal to x squared plus y squared. Right? So that's clear. So if we have a vector AB which takes us x units to the right and y units up, then the magnitude of AB will just be x squared, then the square of the magnitude of AB, right? Because Pythagorean theorem is about the square, not the magnitude itself. Of course, we can just take the square root after that. But it tells us that the square of the magnitude of AB is equal to x squared plus y squared. Now, what I've written here is not quite correct. The convention is not to write just AB arrow squared. What you do is you write AB like this in absolute value, or like in, within these two vertical bars, and then you still put the arrow, and you put the square, to the right of these two vertical bars. That's just some important, but minor um, sign convention or just notation convention. So that's how you find the magnitude. So of course, then what we would do after this is we just take the square root of both sides, and so that's what we get. Notice what we did here though. We found the magnitude of any vector AB. So if I tell you, for example, that the vector AB is, or CD, or just any letters, is 3i minus 4j. How will we find the magnitude of that? Well, we can either think back to Pythagorex theorem and we can say, oh, well, this is 3 units to the right and then 4 units down, and so it looks like this, and so this over here is the magnitude of the vector, and so let me calculate it that way. Or you can just use the formula directly. And so what the formula tells us is that we take the x component, or the horizontal component, which is 3, and we square it, and then we add to that the vertical component, which in this case is -4, and we square that, and then we have all of this under a square root. And so if we find the value of this, well, 3 squared is just 9, and 4 squared is 16. Remember, the negative part will just become positive again after we square it, and so we add 16, and so that's equal to the square root of 25, which is just 5, of course. And so we know, and in this case, you'd also find that it's 5. And so we would know that the magnitude of AB in that case, so we write it like this, that the magnitude of AB is 5. That's perfect. And this 5 could mean 5 kilometers an hour. If we knew that, a certain car is traveling, every hour it's traveling 3 kilometers to the right and 4 kilometers down, then we would know that it's speed, right? Because speed is just about magnitude, or the magnitude of its velocity is 5 kilometers an hour. Okay, now let's think about something else after this. Well, if let's think about, suppose the magnitude of a vector was 1. What does that tell us? Suppose we had some vector AB whose magnitude was 1. Well, that just, that might tell us that a car is traveling at, say, 1 kilometers an hour or something, but sometimes it's useful to force a certain vector to have a magnitude of 1, just so that that vector is only telling you its direction and not its magnitude. Now let me explain what I mean by that. So for this car, we know that it travels 3 units to the right and 4 units down every hour. So it travels at 5 kilometers an hour. That's the magnitude of its velocity. That's its speed. So let's think about now its direction only. How can we figure out what its direction is? Well, what we can do is we can calculate its angle, and we can say, let's assume that this is the north, and so its angle, its direction would be 90 degrees plus theta from north in the clockwise direction, all of that stuff. But that's quite complicated. What we want to do instead is give the direction uh, also in vector notation. So we also say that, because remember, we can find this value of theta and all of these values just from knowing that the fact that the car travels 3 units to the right and 4 units to the bottom every hour. We can figure out all of this information about its direction just from these two values. But these two values also give us the speed or the magnitude of the velocity of the car. Now that might be too much information sometimes if we just want to know its direction. Now, so how do we kind of remove the velocity part if we just want to know the car's direction? Well, here's what we do. We divide by the magnitude. Now let me explain. So AB, the vector AB in this case is 3i minus 4j. This information, what we've written down here, tells us both the direction and the magnitude of AB. Suppose we just wanted to know the direction. We don't want to know the magnitude, and this does happen. Sometimes you just want to give information about the direction and not the magnitude. So how do you do this? Well, you divide by the magnitude. So in this case, we divide by the magnitude of AB. So this is how we write it. But what's the magnitude of AB? Remember, we calculated this. The magnitude of AB is just 5. And so in this case, we would have 3I minus 4j over 5. We can actually distribute this 5 across the 3 and the minus 4, as we're used to. Like, what if we had AB over C? That's just A over C plus B over C. This is something that we're very used to. And so we can turn this into 3/5 I minus 4/5 j. Now you might tell me, well, this is just some silly exercise, why are we doing this? Let's just give them the full value from the beginning. Well, no, remember, the full value also gives the magnitude, and sometimes we don't want to give the magnitude. We just want to know the direction of the car. And so this actually only gives us the direction and not the magnitude, unless the magnitude was, of course, 1, but we don't know that because the magnitude might have not been 1, but we'll still get the same value. Okay, so or the same expression for the direction of AB. Now, how does this only give us the direction and not the magnitude? Well, here's how. If I tell you that it's traveling 3/5 units to the right and then 4/5 units down, that's slightly complicated to understand, but it's just 3/5 and 4/5. Then I'll draw a smaller vector here, AB, and so this is the direction that AB is traveling. In this case, when I've divided by the magnitude. But look, this direction is exactly the same as the direction we had in the beginning, when I went a full 3 units across and 4 units down. It's exactly the same direction. These two triangles are similar. If you wanted to calculate the angles, you'll find that they are exactly the same. But what's the difference now? The difference now is that if we took this small triangle over here and we wanted to calculate the magnitude of the smaller vector AB, we would find that the magnitude would be 1. Okay, how do we know that? Well, we can do that as we are used to. So we can look at the magnitude of this smaller vector AB. I'm using the same name for it, but it's a smaller vector. I'm explaining. And so again, what do? We square the x component, which is 3/5, and we square the y component, which is 4/5, and then we take the square root of all of that. Remember, the square root is important. And then what do we get? Well, 3/5 squared is 9 over 25. Plus still stays as plus. Oh, by the way, remember that this is negative 4/5, but we can just think of it as 4/5 because, as we know, the negative will just cancel. Will just turn into positive when we square it. And the 4/5 part becomes 16 over 25. It becomes, because we square it, and so we square the top part 4, that gives us 16, the bottom part 5, that gives us 25. And so we take the square root of all of that. Okay, how do we work from here? Well, they have a common denominator, and so we can just add the numerators together. When we add the numerators, 9 plus 16, well, that's 25, which is perfect, because then the part in the middle becomes 25 over 25. That's just 1. And square root of 1 is, of course, 1. And so we found that the magnitude of AB squared for the smaller vector is 1. But why is it 1? It's not by magic. We forced it to be 1. Why? Because we forced this 25 to come here at the bottom in order to cancel out with this 25 at the top when we divided by the 5, because we calculated the magnitude of AB in the beginning. When we divided by the 5, we sort of knew that at the end we will divide by 25, which is exactly what we got in order to calculate the magnitude. And so when we divide by the same magnitude, of course it will cancel and give us 1. And that's an amazing thing. And so let's think about a different situation. Suppose we had, the vector AB is 5i plus 5j. Let's just consider this basic case. Well, what's the magnitude in that case? The magnitude would be the square root of 5 squared plus 5 squared, right? We take the square root of x squared plus square root of 5 squared. Well, that's just square root of 50, right? We can work through this. This is 25 over here. This is 25 over here. That gives us 50. Okay, that's fine. We can leave it as 50, or it's better to simplify in this case. 50 is, we need to find the square part so that we can take it out of the square root. So let me just do this. 50 is 25 times 2. So this entire thing becomes square root of 25 times the square root of 2, which becomes 5 square root of 2, right? So this is clear because the square root of 25 is 5. And so if we divide the vector AB by the magnitude of itself, we will get 5 over 5 square root of 2. Okay, let me write this in full. So we have 5i plus 5j, right? That's the vector AB. And the magnitude we found is 5 square root of 2. If we divide the top by the bottom, we get that, these 5's cancel. So we have 1 here and 1 here, but the square root of 2 stays at the bottom. So we have 1 over square root of 2i plus 1 over square root of 2j. Okay, now let's take the magnitude of this, right? Because we want to see if dividing by the magnitude gives us a unit vector. That's what it's called, a vector with a magnitude of 1. So if we try to find the magnitude of this, well, when we square this, what happens? The top part squares, which gives us 1, and the bottom part squares. So the square root of 2 squared, that's just 2, and so we get 1/2. And the same for the second part, which is also 1/2. Remember, again, this is using square root of x squared plus square root of y squared. Now a half plus a half is just 1, and so we get 1 for the magnitude, which is perfect. And of course, this will work in general. Okay, so yeah, let's see now what we need to cover next. So we've gone over unit vectors. Let's look at let's look at points of intersection. Let's look at lines. Okay. Okay. Let's look at lines as vectors. So we know that lines as vectors, and this will be the last thing that we'll go over in this tutorial. So if we think about lines as vectors, well, let's think about lines not as vectors first. I think that's a good idea. So what are lines again? Where lines are, just things that we can draw on this coordinate plane. Suppose we wanted to draw the line y equals x. That's a very basic line that we're used to. It's just the line that goes through the origin here and just passes through like this at 45 degrees. Okay, this is the basic line that we are used to. Now, how can we represent the same line as a vector? So what we can do is we can think about what makes a line a line. What makes a line is that it passes through a certain point with a certain direction. Okay, so it has a slope and it passes through a certain point. I can find many more lines that have the same slope as this line, but they won't pass through the same point. And similarly, I can find many lines that pass through the same point, but don't have the same slope, right? For example, this line, for example. So by having both the slope and the point be the same, I make sure that this is the same line. Okay, so in this case, what is the slope? Well, the slope in this case is 1, right? We can see that because if you go 1 unit to the right, you also go 1 unit up because y is equal to x. So if we wanted to go 1 unit to the right in terms of x, we also have to go 1 unit up in terms of y. If we wanted to go from 0, 0 to 1, 1, which is also on the line, we have to go 1 unit to the right and 1 unit up. So the slope is 1. Okay, that's fine. We can also see the slope because, if it's y equals 2x, the slope would be 2. And that's clear because, if we wanted to go 1 unit to the right in terms of x, so if we increase x by 1, y increases by 2 because you doubled x. So for example, if we went from 0, 0 to 1, 2, we increased x by 1, but we increased y by 2. Okay, it's clear here how we get the slope. Now, how do we get a point? Well, we can just get any point on this line. Obviously, there are infinitely many. But remember, any point that we use, so if I start from this point down here, and I draw a line that has a slope of 1, I would get exactly the same line as if I started at this point over here, and I drew a line that has a slope of 1. And if I started at this point over here, and I drew a line that has a slope of 1. So what I just need to do is to find a point on this line, just any point. In this case, it's very nice that this line passes through the point 0, 0, and so I can just say that the point, I can use that point. You know, I could have used any other point. I can use the point 1, 1, I can use the point 2, 2, any other point, but let's use the point 0, 0 because that's the simplest one. So in this case, for this line y equals x, we have a slope of 1, and it passes through the point 0, 0. Now, how can we represent this as a vector line? So, you know, how can we think of this as a vector line? It's still called a line, but a vector line. So, in order to think of vectors, you always need to think of moving to the right and moving up. So, suppose, yeah, we always need to think of moving right and moving up. So, this line that we have, it must pass through the point. Okay, let me give you the line and then explain to you where it comes from. So the line here, we would say that any point on the line, so any point x, y on the line, remember we represent it like this, this will be equal to 0, 0 plus t times 1, 1. Okay, now this might look quite complicated, but let me explain. Firstly, this 0, 0 part. This 0, 0 part comes from the point that we pass through. We must make sure that we pass through this point, and so we must have it in the equation of the line. Because, you know, if we don't pass through this point and we pass through any other point other than this point, for example, 0, 0, or, you know, whatever other point we chose, and we have the same slope, then that will be a problem because it will mean we're on a completely different line. We need to make sure we're on the same line. And so, you know, the point 0, 0, it has x coordinates 0 and y coordinates 0, and we represent this in vector form as, you know, a 0 on the top and a 0 on the bottom. Okay, this is the point. Now, what is this mysterious t thing that we've added here? Well, the t thing is just any number. So this is just a variable. This is something that we can substitute numbers into. I can substitute 0 into t, and that will give me a point on the line. If I substitute 1 into t, it will give me another point on the line. If I substitute 10 into t, it will give me another point on the line. T is a way of generating points on the line. This is something that comes up a lot in mathematics. You know, you have a variable which you substitute things into and you get things out. And in this case, if we want to find all of the points on the line, the thing that we need to substitute different values of t, and each value of t will give us a different point. Remember, that's because each value of t will give us a different pair of values of x and y. And I'll go through exactly how that happens. Now, this 1 and 1 part, where did we get that from? Well, remember what we said in the beginning. If you had a vector like xi plus yj, well, that involves moving to the right by x and moving up by j. So what does this mean? Well, this means that the slope is y over x. And so if we want the slope of the line to be 1, then we need this part here, the slope part, to also have a slope of 1. Does this have a slope of 1, what we've written here? Yes, it does, because what this says is that for each value of t that I put in, or if I increase the value of t by 1, I am moving to the right by 1, and I am moving up by 1. Well, if I'm moving to the right by 1 and moving up by 1, that means that I have a slope of 1, right? Because slope is rise over run. Now, you could tell me here, okay, Ahmed, can't I put a 2 here and a 2 here? Well, yes, you can. If you put a 2 here and a 2 here, you will get a rise of 2, and you'll get a run of 2. And since since the slope is rise over run, the rise over run in this case will be 2 over 2, which will also be 1. That's fine. But sometimes using 1 and 1 is simpler for you, right? Because by using 1 and 1, as we will see, you know, it just it makes it easier to find all of the points on the line. And we'll go through how that happens, but just know that you are allowed to use 2 and 2. Now you might come here and say, well, can I use something different for the point that I start with? And as I said, yes, we can. We can use 1 and 1 for this point part, or we can use 2 and 2 for this point part. Why can we use these things? Because in this point part over here, we just need a point that lies on the line, any point. So 1, 1 lies on the line, so I could put 1 here and 1 here as well. That's fine. I just need any point that lies on the line. But it's best always to choose the simplest option in every case. And in this case, the simplest option for the point is 0, 0. And the simplest option for the slope part is 1, 1. Because 1, 1, as we said, gives you a slope of 1. Right? Because you put the rise part over the line. And it gives you 1, which was the original slope of the line. Okay, let me go back to the t part very quickly and explain to you how we generate points on the line. Remember, I told you that by putting in values of t, you get points out. Let me do that for you. Let's go back to our basic form of line, which is xy is 0, 0 plus t times 1, 1. Let me substitute t equals 0. What does this mean? Well, this tells me that xy is equal to 0, 0 plus 0 times, remember this is a times over here, but you don't have to write the times, of course, times 1, 1. So this is telling me that I am moving 0 times 1 to the right and 0 times 1 up. Well, 0 times 1 to the right is, 0 to the right, and 0 times 1 up is 0 up. And so this entire thing just becomes 0, 0, right? You basically distribute the number that you have at the top here, that you have at the front here, into both of these numbers. So this is actually an important thing to know about vectors in general, which is that if you have k times a vector AB, then this is just equal to k times A and k times B over here, right? Because if you're moving k times A to the right, then it's like moving k times A to the right at once, rather than moving to the right by A, and then to the right by A, and then to the right by A k times. You can just move to the right by k times A once, right? So, and similarly for B. And so this is something that's useful here when evaluating points on lines. And so by distributing the 0 here, we get 0, 0. And so what we have is 0, 0 plus 0, 0. Well, if I am moving 0 to the right in this part, and then 0 to the right, and then adding to that another 0 to the right, well, I just get 0 to the right. And then similarly here, if I'm moving 0 up, and then adding another 0 up, then I'm just moving 0 up. And so, we'll just get 0, 0 overall from this. And now what is this telling us? Well, this is telling us that x over here, look over here. It's telling us that x is equal to 0, because we can equate the x part to the x part from here. And we can equate the y part to the y part from here, because the x over here tells us by how much we move to the right. And this says that we move to the right by 0. That means that x must be 0. And this says that we move to the right by, move up by 0. And so y must be 0. So that's clear. So in this case, this gives us that x is equal to 0 and y is equal to 0. Now notice what we've done. We've just substituted the number into t, and we've got out two numbers, one for x and one for y. And what do these numbers represent? Well, these numbers represent the coordinates of a point on the line. These two values correspond to the point 0, 0, which we expect to be on the line. And yes, it is, right? This in the line y equals x, which we started with, the point 0, 0 will be on the line. Okay, let's, in order to conclude, just try one more line, one more point, one more value of t. So suppose I use the value of t, say, of 1/2. Let's use the value of 1/2. Well, remember, the vector equation of the line is 0, 0 plus t times 1, 1. Now let me substitute t. That gives me 0, 0 plus 1/2 of 1, 1. Again, using this rule that we had over here, which makes sense to us, right? Because, as I said, we can think about doing multiple steps as just doing one big step. So in this case, we distribute the 1/2 into here and the 1/2 into the bottom. And so it gives us 0, 0 plus 1/2 at the top, because 1/2 times 1 is 1/2. and then 1/2 at the bottom, because 1/2 times 1 is again 1/2. And if we add the moving to the right bit from this vector to the moving to the right bit from this vector, we will get again 1/2 in terms of moving to the right. Let me explain this part more clearly. This vector over here, it tells us move 0 to the right. Okay, that's very nice. So I'm not moving at all. And then this vector over here, it tells us, oh, move 1/2 to the right. Okay, so I move 1/2. I add to what I've done before. Well, by moving 0 to the right and then moving 1/2, overall I've moved 0 plus 1/2, which is just 1/2. Notice that if this number over here was 1, if we chose the number 1, 1 to start with, then we would get a different value here. We would get 1 plus 1/2, which would be 3/2. But that's not what we have. We chose the number 0, 0 because they were simpler for us. So we just continue with that. So again, similarly for the y part, we start at some point and then we add 0. We go up by 0. Oh, that's just staying at the same point. And then we go up by 1/2. So that's going by 1/2, up by 1/2 slightly. And so we get 1/2 in this part again overall. 0 plus 1/2. And so that tells us that we get the point 1/2, 1/2. Now, does this make sense? Yes, it does, because the point 1/2, 1/2 does lie on the line, which we were trying to represent in vector form. So overall today, what we covered is that, these vectors are a way of describing are quantities that are used to describe the magnitude and direction of something, like a velocity. We went over the different forms that they can have, so AI minus BJ, or just this AB notation on top of each other. We went over the interesting equation of how AB is the same as OB minus OA. If you have the expressions for OB and OA, from a reference point, some origin O. We also went over the magnitude of a vector. We said that it was the square root of x squared plus y squared, coming from Pythagorex Theorem. We also went over unit vectors and how they describe to us the direction of a vector only. And lastly, we went over how we can find out, how we can turn Cartesian equations, or equations with y's and x's for lines, into vector equations with like this t and these vector expressions. Okay. Now let me see if we have any questions here. Okay, I can see that there's a question here. How about knowing whether or not vectors are aligned in one line? Oh yes, this is an interesting point as well. This is about collinear vectors. So what you can do for collinear vectors is so what are collinear vectors? Well, they are vectors that like lie on the same line. So they have the same direction, but they can also have like the negative of that same direction. So so suppose you had a vector AB over here, and you wanted to find whether the point C was on the same line as AB. What you would do is you would check whether the vector AB is parallel to the vector AC. Now, how you do that, you can find the slope of both, right? You can take the y component of AB, because it will be of the form xi plus yj. You can take the y component of that divided by the x component, and similarly for the vector AC, and see whether you get the same answer for both. If you do, then you know that AB and AC are parallel. Now, if AB and AC are parallel, that means that AC or the point C must lie on the vector on the line AB, because C is on the line that passes through A and has the same slope as this line over here, and every line is only given by a point and a slope, and so the line AC must be the same as the line AB, because both of these lines have the same slope and pass through the same point A, and so that tells us that points A, B, and C are collinear. So that's one way of figuring out whether or not points are on the same line. or that points are collinear. Hopefully that answers the question. Okay, no questions, so that's perfect. And that brings us to the end of the live stream. Thank you all for watching, and